So in the Chapter 5 quiz review, we're going to review probability distributions for proportions and means when the sample size is bigger than 1. So in our first problem, we have that the Gallup poll once asked a random sample of 1,540 adults, do you happen to jog? Suppose that in fact 15% of all adults jog. Find the mean and explain how you know. So we know the mean of a sampling distribution for proportions and means is equal to the population, which in this case is 0.15. And the reasoning behind that is not because the sample proportion is equal to the population portion. It is, but it happens to be because the distribution has to be random. So because the sample is collected randomly. So remember, as long as you mention randomness somewhere, then the mean of your distribution equals the population. The next one says to calculate the standard deviation of p hat in this setting and explain why you can use this formula. So the formula for the standard deviation of a sample proportion is the square root of p times 1 minus p all over n. And you do not have to memorize this formula. It is something I will give you for the quiz. So for us, our sample, our p is 0.15 times 1 minus 0.15 all over n, which is our sample size, 1,540. And that's going to give us 0.0091. And then why we can use this formula is the 10% condition. So the 10% condition says that your sample size, in this case 1540, has to be less than or equal to 10% of your population, which would be all adults. And again, we don't have to know the population size to know that this condition is met, because if I multiply my sample size by 10, I get 15,400, and I know there's at least that many adults. So the formula, little n less than or equal to 10% of big N. That's the 10% condition. And then last one is check that you can use the normal approximation for the distribution of p hat. To determine if something is normal, NP has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. So you have to make sure you have enough successes and failures in your distribution. So we're going to do 1540 times 0.15, and then 1540 times 1 minus 0.15. And both of those have to be greater than or equal to 10. Now remember, I said that the only time you really have to worry about this condition not being met is if your sample size is close to 100, especially if it's less than 100. That's the only time this condition really has a chance of not being met, because 15% of 1,540 is over 100 and, well, I think it's over 200, because 10% is 154. So 15% is definitely going to be greater. So then 1540 times 1 minus 0.15, also greater than or equal to 10. The last part says to find the probability that between 13 and 17% of the sample jog. So remember the 4 steps that you have to include in a problem. You have to write the probability statement. You have to calculate your mean and standard deviation. If I don't already ask you to do that in a previous problem, then you have to do the probability itself and your sentence. So I'll have 0.13 less than or equal to p hat less than or equal to 0.17. I'm just going to rewrite my mean and standard deviation that I've already calculated. Okay. Then we're going to do normal CDF, and because we're between two values, my lower bound is 0.13, upper bound 0.17, mean of 0.15, standard deviation of 0.0091. and we end up with 0.9720. You do not have to show the work for calculating your probability. Like, I don't have to know what you type into normal CDF. However, if your probability is incorrect and I don't know what you plugged into the calculator, there's no partial credit that can be earned for the probability itself. So it's always to your benefit to go ahead and write what you typed into the calculator just so I can give partial credit. And then for our sentence, we can say the probability that in a sample of 1,540 adults between 13 and 17% of them jog is 0.9720. You are also allowed to write your sentence using percentages. So you can say there is a 97.2% chance that between 13 and 17% of the sample jog. So I don't care if you leave it as a probability, do it as a percentage, as long as your sentence talks about that and writes the context of the problem. In our next example, we have that about 75% of young adult internet users, so that's ages 18 to 29, watch online videos. Suppose that a sample survey contacts an SRS of 1,000 adult internet users and calculates the proportion in the sample who watch online videos. So what is the mean? So exact same as the previous problem. So the mean is going to be 0.75, and that would be because we are taking an SRS. So again, randomness or taking an SRS, both of those mean the same thing. That is the reasoning behind our sample proportion, mean of our sampling distribution being 0.75. And then the standard deviation is going to be the square root of 0.75 times 1 minus 0.75 all over 1,000, which is going to be 0.0137. And then checking our 10% condition. So 1,000 has to be less than or equal to 10% of all young adult internet users. And again, I don't have to know what that population size is, but I do know that it is going to be greater than 10,000. And then C asks us again to check that we have a normal distribution. So 1,000 times 0.75 and 1,000 times 1 minus 0.75 have to be greater than or equal to 10. And that's going to be 750 and 250. So both of those are met. D is a little bit different on this one. So instead of actually asking for a probability calculation, I ask if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? So there are two things that are always affected by changing your sample size, and that's going to be your standard deviation and your shape, because both of those rely on n, which is your sample size. So standard deviation, in this case, anytime you increase your sample size, you decrease your standard deviation. So standard deviation is going to decrease. And then the other one would be if the shape changes at all. In this case, it can't become more normal, it just would stay normal. So the only time you really have to mention the shape changing is if it wasn't normal to begin with. So like if my sample size to begin with was 75 instead of 1,000, then I would say, well, my distribution isn't normal, so increasing it to 9,000 is going to make it normal. So you really only have to mention the shape if it's not normal to begin with. In our third example, we have that a sample survey interviews an SRS of 267 college women. Suppose that 70% have been on a diet within the past 12 months. What is the probability that 75% or more of the women in the sample have been on a diet? So we're going to have probability of p hat greater than or equal to 0.75. One question I often get is, how do you know if you have a mean or a proportion? Proportions are always percentages. So you're gonna have a percentage that the question is asking about in the problem. Means do not. So that's the biggest difference. A proportion is a percentage, mean isn't. So the mean of our sampling distribution is going to be 0.70, and then our standard deviation is the square root of 0.7 times 1 minus 0.7 all over 267, which is going to be 0.028. Then we go to normal CDF. Our lower bound is going to be 0.75. Upper bound is the 9s, or 1E99. Mean of 0.70. Standard deviation 0.028. And we are going to get a probability of 0.0371. So we can say the probability that in a sample of 267 college women, 75% or more, have been on a diet in the last 12 months is 0.0371. In our next example, we have a Gallup poll asked a random sample of 1,785 adults whether they attended church during the past week. Let p hat be the proportion of people in the sample who attended church. A newspaper report claims that 40% of all US adults went to church last week. Of the poll respondents, 44% said they did attend church last week. If the newspaper claim is true, what is the probability that random sample of 1,785 adults would have a sample proportion equal to 44% or more? Does this give convincing evidence that the newspaper's claim is true? So a lot going on. So the first thing I'm going to do is write my probability statement. And it's always best to look at the question to help with your probability statement, because the percentage used in the question is the percent that goes with your probability statement. So we're trying to see the probability that p hat is greater than or equal to 0.44. So then the other percentage is going to be your mean. So mean of p hat is 0.40. Standard deviation, 0.4 times 1 minus 0.4 all over 1,785, which is going to give us a standard deviation of 0.0116. So we do normal CDF. Lower bound is 0.44. Upper bound is the 1E99. Mean of 0.40. Standard deviation 0.0116. And remember, I told you guys when we did these in notes, you have to pay attention to scientific notation, because our answers are probabilities, which means they're always going to be between 0 and 1. So if you get a number bigger than 1, you always go to the end and you look to see what the scientific notation is. So in this case, we're going to get 2.82 and then E negative 4. So that means is you need to move the decimal place to the left 4. So it actually becomes 0.000282. A little shortcut for this is whatever the number is after E, 1 less 0 after the decimal place for your probability. So to answer our question, does this give convincing evidence that the newspaper's claim is true? We would say this does give convincing evidence because the probability in a sample of 1,085 that 44% or more attended church last week is very small, and then 0.000282. Next example says, according to a poll, 22% of high school students in the United Kingdom say that Dobby is their favorite character in the Harry Potter books. Let's assume this is the parameter value for the entire population of high school students in the UK. You take a sample of 150 high school students and record the proportion of individuals in your sample who say Dobby is their favorite character. What is the probability that the sample of 150 high school students has more than 25% of them saying Dobby is their favorite character? So we do probability p hat greater than 0.25. Our mean is going to be 0.22. Standard deviation will be 0.22 times 1 minus 0.22 all over 150, which is 0.0338. So we go to normal CDF, lower bound 0.25, upper bound is the 1E99, mean 0.22, standard deviation 0.0338. And we're going to get 0.1874. So for our sentence, the probability that in a sample of 25 high school students in the UK more than 25% say Dobby is their favorite character is 0.1874. And again, your sentences do not have to be written the exact same way as mine, as long as you mention that it's a probability or a percent. If you convert it to a percent, you restate the problem or the question being asked, and you give your probability or percentage. That's all that is required in your sentence. So next we're going to look at some examples with means. So we have that the distribution of actual weights of 8-ounce chocolate bars produced by a certain machine is normal, with a mean of 8.1 ounces and a standard deviation of 0.1 ounces. Company managers do not want the weight of a chocolate bar to fall below 7.85 ounces for fear that consumers will complain. So we want to find the probability that the weight of a randomly selected candy bar is less than 7.85. So this is dealing with a single candy bar. So you have the probability that X bar is less than 7.85. So we're dealing with a single candy bar. Our mean is whatever the population mean is, which is 8, and our standard deviation is whatever the population standard deviation is, which in this case is 0.1. So then we go to normal CDF, lower bound negative 1E99, upper bound 7.85, mean of 8, standard deviation of 0.1. And we're going to get 0.0062. So it's very, very unlikely that a single candy bar is less than 7.85 ounces. And as we know from when we did this previously, that whenever you increase your sample size, it decreases the probability because our standard deviation is going to get smaller. So I'm going to do this again later with a higher sample size, and we'll see how much the probability is going to decrease from increasing our N. So we're going to check our conditions for selecting 4 candy bars. So it's a little bit harder to see, tell what our sample size here is because it's written instead as a word instead of a number. So make sure you're paying attention to that type. So for means, random and independent are the same conditions for means and proportions. So it does say that they are selected at random. Okay. For independent, our sample size 4 has to be less than or equal to 10% of our population, which would be all 8-ounce candy bars. And again, I don't need to know how many there are, but I can almost guarantee that there's at least 40. So we should be good there. And last is normal. So this is where means and proportions differ. Because for means, it has to meet, for normal, it's one of 2 things. Either the population has to be normal, or the sample size has to be greater than or equal to 30. In this case, our sample size is 4, which does not work. But it is stated that the population is normal. Both can be true, but one of them has to be. So now we're going to recalculate our probability for our sample size of 4. So the only thing that's going to change is our standard deviation. So we're still doing the probability that X bar is less than 7.85. And our mean of our sampling distribution is still 8, but the standard deviation is now the population standard deviation 0.1 over the square root of N, which is 4. And again, this is not a formula you have to memorize. I will give it to you, and we get 0.05. So when we do normal CDF, lower bound is our negative 1E99. Upper bound is 7.85. Mean of 8. Standard deviation 0.05. So basically our standard deviation was cut in half by our sample size. And our probability becomes 2.87 E negative 7. So that's going to be 0.000000287. So we can see increasing our sample size from 1 to 4, which only decreased our standard deviation by half, affected our probability pretty significantly, which is why we always like to do sampling distributions and have sample sizes that are large instead of looking at a single one. In our next example, we have that the weights of newborn children in the United States vary according to the normal distribution, with a mean of 7.5 pounds with a standard deviation of 1.25 pounds. What is the probability that in a random sample of 20 babies born at a large local hospital, the average birth weight is below 7 pounds? So we're looking at the probability that X bar is less than 7. So our mean is 7.5, and our standard deviation is going to be 1.25 over the square root of 20. So remember, when I do standard deviations for means, because they could be over 1, I will only go 2 decimal places if the number is bigger than 1, but if it is still less than 1, I keep 4 decimals. So in this case, 0.2795 is obviously less than 1, so I'm going to keep 4 decimal places for my probability. Standard deviation in calculating the probability. So normal CDF, lower bound is going to be our negative 1E99, upper bound 7, mean 7.5, standard deviation 0.2795. And that's going to result in a probability of 0.0368. So for our sentence, the probability a sample of 20 babies at a large hospital has a mean birth weight less than 7.5 pounds is 0.0368. So not very large. This hospital has lots of heavy babies. Next one is going to be slightly different. This is more like the end of section 1, where we were looking at multiple distributions and combining them. So we have a women's swim team, and we have times for the 400-meter freestyle relay, where they swim 100 meters, and we have the times in seconds for the 4 swimmers, and they're approximately normal with the means and standard deviations. Assume that the swimmers' individual times are independent. Find the probability that the total team time is less than 220 seconds. So we're trying to find the probability X bar is less than 220. So the mean of this sampling distribution is calculated pretty straightforward. You just add them all together. So the mean of X bar is going to be the means of all 4 added together. Which is going to be 224.2. Standard deviation is slightly different. So the standard deviation is the square root of the sum of each standard deviation squared. So it's the square root of 2.8 squared plus 3 squared plus 2.6 squared plus 2.7 squared. We're going to get 5.56. So even though the mean and standard deviation are slightly different, we then do normal CDF just like normal. So the lower bound is going to be negative 1E99. Upper bound is the 220. Mean is 224.2. Standard deviation 5.56. And we get 0.225. So the probability that the relay team takes less than 220 seconds is 0.225. It's a pretty decent probability, considering most of the time our probabilities are 0.0 something. So 0.225 is pretty decent. All right. So the last examples that we have to look at are for the differences in means and the differences in proportions. Now I don't have an example of a difference in proportions here, but they work very similarly. You just have to use the standard deviation formula that's going to be stated on the formula sheet. So I'm only going to do an example of a difference of means, but you can look back in the notes for an example for a difference of proportions. So we have some variable from two populations that has a mean of 40 and a standard deviation of 24, and then the second population has a mean of 40 and a standard deviation of 20. And the variable is normally distributed in each of the two populations. So we have samples of sizes 4 and 16, and we want to know the mean and standard deviation for the difference in our distribution. So the mean for the difference in x1 minus x2 is just the subtraction of each mean. So we do 40 minus 40, which is going to be 0. The standard deviation, we have to use the standard deviation formula. So that's the square root of standard deviation 1, which is 24 squared, over its sample size, which one of them is, the first one is 4, plus the second standard deviation, 20 squared, over its sample size, 16. That's actually going to give us 13 as our standard deviation. The next question says, can you conclude that the variable is normally distributed? Explain your answer. So for means, just like with a single mean, either each distribution is normal for the population, so the difference is normal, or each sample size has to be greater than or equal to 30. So the answer here is yes, because each population is normally distributed. And then one thing you do want to remember when I have you do a difference of means or difference of proportions problem, you have to define your variables. So you have to let me know which one is x1 and x2, because it's going to affect how you set up your probability statement, how you calculate your mean. The standard deviation, the probability themselves will be the same, but your mean and probability statement are based on how you define x1 and x2. So let's go ahead and figure out the probability that for whatever our populations are, that the difference is between negative 13 and positive 13. So we're doing the probability negative 13 is less than x1 minus x2 is less than positive 13. And then we know the mean is going to be 0 and the standard deviation is going to be 13. So we do normal CDF. Lower bound is negative 13. Upper bound is positive 13. Mean is 0. Standard deviation of 13. And we're going to get 0.6827. And then because it says percentage, that would be 68.27%. Very rarely do I actually ask for a percentage. Most of the time it will stay probability. Next, we have some multiple choice practice. So remember, the only time that you're going to have to check conditions is going to be on a multiple choice question. I might ask you to tell me which condition isn't met, or ask you for a specific condition to check. So that's the only time that you really have to know conditions, is on a multiple choice question. So we have an SRS of size 64 from a population with a mean of 50 and a standard deviation of 2. We want to know, does the population need to be normally distributed for the sampling distribution to be normally distributed? And so the only time that the population has to be normal is if your sample size isn't bigger than 30. And because our sample size is 64, that automatically leads me to no. So I can get rid of the ones that say yes. And then it has to do with sample size. So I can also get rid of E because it talks about the population mean. So that leaves us between B and C. So B says no because the central limit theorem states that regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size N increases. And C adds in that the shape of the underlying population is normal or uniform. And the key difference there, it's saying uniform, is why the answer is going to be B. Because it's not uniform. Uniform would mean that every value is the same. And the central limit theorem only mentions the population being normal. In the next one, we have that a population has a normal distribution with a mean of 50 and a standard deviation of 10, random sample size of 9. What is the probability that the sample mean will be between 48 and 54? The biggest mistake I see on multiple choice questions where you have to calculate a probability, especially with means, is people don't calculate the sample standard deviation. They use the standard deviation from the problem. So I actually have to first calculate the standard deviation, which is going to be 10 over the square root of 9, which is going to be 3.33. Then you do normal CDF. And then our lower bound is 48. Our upper bound is 54. Mean of 50. Standard deviation 3.33. And that's going to be 0.611. Next problem says a random sample of size 16 is to be taken from a normal population, has a mean of 100 and a standard deviation of 2. What value represents the 90th percentile of the distribution? So this is an example of INV norm. We didn't really do a lot of INV norm in this chapter. It's not likely to be on the quiz, but anytime you're given a percentage, you want to do the percentile, that is the area below. So the area is 0.90. And then our mean, 100. And then again, do have to calculate the standard deviation for the sample size. So 2 over the square root of 16, which is going to be 0.5. And then for those of you who have the option, the tail will be to the left because it is percentile by definition is the area to the left. We're going to get 100.64. Next, we have the average number of push-ups a U.S. Marine does daily is 300 with a standard deviation of 50. Random sample of 36 Marines is selected. What is the probability that the sample mean is at most 320 push-ups? So again, standard deviation has to be calculated. So 50 over the square root of 36. It's going to be 8.33. And then we can do normal CDF. Lower bound is the negative 1E99. Upper bound 320. Mean 300. Standard deviation 8.33. And we're going to get 0.9918. On a multiple choice question on the quiz, you don't actually have to show me your work. I'm only doing it here so you know how I arrived at the answer. It's multiple choice. You're not given partial credit for showing your work. so the work doesn't matter. So you can do it all in your calculator, and I'm not going to need to see the work. Last one says, let the random variable x represent the weight of male black bears before they begin hibernation. Research has shown that x is approximately normally distributed with a mean of 250 pounds and a standard deviation of 50. What's the probability x is greater than 325? Because we do not have a sample size greater than 1. This is just for a single bear, so I can go straight to normal CDF. Lower bound 325, upper bound is the 1E99, mean 250, standard deviation 50. So generally speaking, if you're going to decide, do I have to calculate my standard deviation or not? If I give you an n, you have to calculate standard deviation at some point. If you're not given a sample size n, you can use whatever you're given. So you get 0.0668, which is A. All right, so next we're going to use the same problem for 15 and 16. So we have that the magazine Sports Illustrated asked a random sample of 750 Division I college athletes, do you believe performance-enhancing drugs are a problem in college sports? Suppose that 30% of all Division I athletes think that these drugs are a problem. Let p-hat be the sample proportion who say that these drugs are a problem. Which of the following are the mean and standard deviation of the sampling distribution of the proportion? Well, first things first, we know that the sample proportion is equal to the population proportion. So it has to be 0.30. So that eliminates D and E. So then I just have to calculate my standard deviation, which is 0.30 times 1 minus 0.30 all over 750. And then you take the square root. And you get 0.0167, which is going to be A. Next one asks, the sampling distribution is approximately normal because, so when you have a proportion, remember you have to check that NP is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. Both of these have to be true. So when I plug in N and P, where N is 750 and P is 0.30, N times P is 225, N times 1 minus P is 525, and they are both at least 10. So the answer is going to be B. A is the 10% condition, so it's actually testing that they're independent. C would be random. And then D and E are kind of like your throwaway options. All right. There aren't going to be any true-false questions on the quiz itself, but it could be kind of a situation where I basically ask you for the definition of something. So I'm still going to go over it. So a parameter is a number that describes a population. So that is true. Parameter is something that describes the population. Statistic describes your sample. Next one says a statistic is biased if the spread of the sampling distribution is not equal to the true value of the parameter. And this is false. So a statistic is biased if the sampling distribution is not normal. Random, sorry. So as long as you have randomness, you don't have to worry about it being biased. The 10% condition makes sure our sample size is less than 10% of our population size. That is true. If the population distribution is normal, then the sampling distribution is normal. Now, this is true with a little asterisk. It should say for means. So this is for means only, it's true. I would make sure to specify if I was talking about means or proportions on the quiz. So this should say, if the population distribution is normal for means, then the sampling distribution is normal, in which case it's true. Last one, if the population distribution is not normal, the central limit theorem says that the sampling distribution of the sample mean will be approximately normal if, in most cases, if NP is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. This is false. Everything up to the last statement, because that is for proportions. For means, it's that N is greater than or equal to 30. Let me know if you have any questions about anything in preparation for the Chapter 5 quiz.